Hi everybody, this is Poisson from AUA with probability lecture number 33. And today we're gonna cover the topic of independence of random variables. So independence of random variables. So in our previous lectures we have considered random variables and talked about their transformation. So applying some function to that x and getting new random variable. So y is our new random variable obtained by applying some function g to x. And of course, having x and this transform of x, we can say for sure that y depends explicitly on x. So x and y are dependent in this case. In this case, if I know the value of x, then I will know for sure the value for y, of course. Now, if we have general jointly distributed random variables x and y, so x and y are jointly distributed random variables, that is, x and y are just random variables defined on the same sample space, on the same experiment. It can happen that even if we will know the value of x, y can take different values with different probabilities and distribution. So let me give an example. Say if we will consider the following discrete case, x is taking two values 0, 1, y is taking only two values 0 and 1. And with this PMF probability mass function, then if x is 0, so if x is 0, then we can have both y is 0 and y is 1. So it is possible for, if we know that x is 0, then it is possible that y can be 0 or y can be 1. Of course, the probability of having 1 if x is 0 is twice as more as the probability of having 0. So the chances of having 1 versus 0 will be 4 to 2 or 2 to 1, of course. So how we can measure if x and y are dependent or not in this case, if for each value of x we can have different values of y, say, like in this case. First, we call that when talking about joint distribution of random variables, we noted that knowledge of their the joint PMF or PDF of this random pair random vector x, y is not only giving the individual marginal distributions of x and y, but also giving information about their relationship. So pictorially, if we have the joint distribution of x and y, then we have the following. So we have the distribution of x, marginal distribution of x. We have the marginal distribution of y. Also, we have the dependency or relationship between x and y. So this encompasses in itself the distribution of x, distribution of y, also the dependency relationship between x and y. But also we have noted that the inverse is not true in general. So having individual distributions of x and y, having marginal distributions, is not enough to give their joint distribution. And in particular, having only the distribution of x and distribution of y, it is not enough to be able to calculate this kind of probabilities. So if we have the distribution of x and we know the distribution of y, that is not enough to find the joint distribution of x and y. Let me give example. Say, assume that x and y are identically distributed Bernoulli 0.5 random variables defined on the same space, sample space. That is, x and y are taking values 0 and 1 with probability 0.5, 0.5. Then in that case, we can have infinitely many joint probability mass functions or infinitely many distributions such that x and y are marginals of that PMFs. For example, we can have the following case. Say, if x and y have this joint PMF, then the marginals are, of course, 0.5, 0.5, 0.5, 0.5. So if I will try to write marginals here, so what I will have, sorry, yeah, so I will have this kind of thing. So here I am writing the probability that y is equal to that particular value y, small y can be either 0 or 1. And I'm adding these two numbers and I'm writing it here, 0.5 and 0.5 here. And for the marginal of x, I'm writing it in this margin, so probability that x is equal to x, and I'm writing column sum here, and this column sum here. So y is taking values 0 and 1 with probability 0.5, 0.5. These are not minus signs, but I was just showing that number, sorry. 0 and 1 with probability 0.5, 0.5, and x is taking 0 and 1, that values with probability 0.5, 0.5. So in this case, for this joint PMF, marginals are exactly these ones. But this is not the only case. So if we will consider this one, so I have switched the places of 0.5s and zeros. So again, if you will calculate the marginal distributions, then you will have the same Bernoulli 0.5 for x and y. And even more, if you will consider this one, so 0.2, 0.3 here, we have 0.5, 0.5 here, 0.5 here, and 0.5 here. So marginals of this are, again, Bernoulli 0.5 random variables. So in fact, only having these two distributions of x and y is not enough to reconstruct the joint PMF, the total distribution relationship between x and y, encompassing also the relationship between x and y. By the way, you can construct, in fact, infinitely many these kind of joint PMFs having these marginals. Try to do that. Okay, so to completely describe the joint PDF, uniquely describe the joint PDF, we need to have first distribution of x, of course, distribution of y, and we need to have the dependency or relationship between x and y. In that case, we will have the joint distribution of x and y. In fact, giving this means, well, describing that joint distribution of x and y, in fact. So describing dependence, in fact, or relationship between two or more random variables is not an easy task at all. One needs to have the joint distribution to have a complete knowledge about that relationship. But in practice, one rarely has that joint distribution. So usually people start from the basic type of dependence. So very special case, but also very important one. So very special type of dependency where there is no dependency at all. So where our random variables are independent. So today we're gonna cover that independence case. So, and in many studies, people are assuming independence between measured quantities or approximate that calculations through independent quantities. So here we will consider that independence notion, study properties of independent random variables, use independence to calculate probabilities. And later in our next lectures, we will consider introduce two measures for dependency, covariance and correlation. They are measuring linear dependency between two random variables. Let's keep that for our next lectures and today cover that independence case. So here in this lecture we will consider joint distributions obtained in the following way. So we have the distribution of x, we have the distribution of y, and we have this dependency. So x and y are independent. So this will completely describe our joint distribution of x and y. So we will assume that this is our case, and we will find joint distribution, and having that joint distribution we can calculate probabilities, etc. First, some examples for getting that ideas. Discrete cases. So, example, assume that joint PMF of x and y is given through this table. So, x is taking values 0 and 1, y is taking values 7 and 9, and the probabilities are 0.3 for x0, y is 7, etc. So, we have this table, 0.3, 0, 0, 0.7. So, what can be said about the relationship between x and y? So, if I know that x is 0, say, if I know the value of x, then that is giving information about y. So if I know the value of x is 0, then only these two can happen, 7, 9. But because the probability of having value 9 for y is 0, then I can have only this case. So if x is 0, then y can be only 7. And if I know that x is 1, then y can be only 9, because this probability is 0, having the probability that y will be 7 and x will be 1 is 0. So knowing knowing the value of x is giving complete information about the value of y. So we can write this in the following way. Say x is taking two values 0, 1 with probability 0.3, 0.7, and y is given, say, through this formula, 2x plus 7. Say if x is 0, then I will have y is 7. If x is 1, I will have y is 9, and I will have this joint PMF for this case. Or we can take any other function of x giving that 7 and 9 at these 2 points. So in this case, y depends on x, of course, clearly, because knowing x, we are for sure calculating the value of y. Now another example, another pair of random variables. Assume x is taking these 3 values, y is taking these 2 values, and this is our joint PMF. So let's think about the relationship between x and y. So assume I know the value of x. If x is 0, then y can be both 7 or 9, and the chances odds against 7 against 9 is 0.3 to 0.2. So 3 to 2 chances of having 7 value versus having 9 value for y. So 2 chances. In fact, we can calculate what is the probability in that case that y will be 7. That is, we are calculating, in fact, we are calculating the probability that y will be 7 given that x is equal to 0. And how to calculate this probability? We are just calculating their sum. So this sum is 0.5. And the probability that y will be 7 is 0.3 over that sum 0.5. So 3 over 5. We could calculate that also from this. If chances are 3 to 2, then 3 over 5 for the probability for the first case, and 2 over 5 probability for the second case. Okay. So knowing the value of x, this property gave us, if x is 0, this knowledge, this information, sorry, gave us the following. If x is 0, then y can be either 7 or 9, and the chances of having 7 is 3 to 2 versus having the value 9. Okay. If x is 1, what is that giving? If x is 1, then again y can take both values 7 and 9, but the chances are 1 to 2. So 1/3 probability that I will have 7 in that case, and 2/3 probability that I will have 9. And if x is 2, then chances are equal that y will be 7 or 9. So what this means? So if we will know the value of x, that will change our information about the distribution of y. So if I know x is 2, then the distribution of y is equiprobable, uniform, discrete uniform, because it has same chances for 7 and 9. Probabilities are 0.5. So 0.1 over the sum 0.2, which is 0.5. If I know, say, that x is 1, then the chances are 1 to 2 of taking these values. So knowledge about, information about x is changing to probability of y. Even more, without any prior knowledge about the value of x, we can calculate what are the probabilities for y for taking these values 7 and 9. That is, I'm calculating the marginal distribution of y. So marginal distribution of y is this sum 0.5, this sum 0.5. So without any knowledge about x, y can take values 7 or 9 with probability 0.5, 0.5. This is given through this PMF. So these probabilities are 0.5. But if we learned that x is 0, if we know, we have information that x is 0, then that probabilities of having the value 7 or 9 are changing, because now I have 3 over 5 probability of having 7 and 2 over 5 probability of having 9. That is, our information about x is changing the probability of having particular values for y. That means that y depends on x. And similarly, if we will fix the values of y, say I know that y is 7, what is happening with x? X is taking these 3 values with corresponding probabilities. So I need to divide this 0.3 to this sum 0.5. Okay. Or what if I know that y is taking the value 9? Then I will have another thing. Then knowing the value of y will change the probability of x. Say, if I know that y is 7, I will get different distribution for x for taking these values than if I will know that y is equal to 9. Or if I will not have any prior knowledge about the values of y. In that case, x will take the value 0, 1, 2 with probability 0.5, 0.3, and 0.2, the marginal of x. So in that case, we had dependence, because the knowledge about one of the variables was changing our distribution for the other one. Now, assume that joint PMF of x and y is given through this table. So x is taking the same values, y is taking the same values as in our previous example, but the probability of this PMF is another thing. So let's see what is happening in this case. So if x is 0, then y can take both 7 and 9 with some probabilities, and the chances that it will take 7 versus 9 are 4 to 6, that is 2 to 3 for 7 versus 9. That is, with probability 2 over 5 it will take the value 7, and 3 over 5 it will take the value 9 if we know that x is 0. Now what if we know that x is 1? So if we will calculate the same chances, the same odds in this case, then we will have the same number, 0.12 over 2, 0.18, which is giving 2 to 3. So the same chances of having this versus that. And if we will consider the case when x is 2, say we know we have some information that x is 2, then we will have again the same chances, 0.24 to 0.36, which is again 2 to 3 for having 7 versus 9. So even we can think like this, even you can continue, say I know that x is less than 1.5. This is my information. What are the chances for y taking 7 versus 9? You will get the same thing if you will calculate. Okay? So this means that the information about x is absolutely not changing the probability, the distribution of y, of taking these values 7 and 9. Even without any prior knowledge about x, if I will consider just the distribution of y, the marginal distribution of y will be, here I need to write the sum of these 3 elements. So this will give 16, 0.4, and here I need to have 0.6 to have in the sum 1. So you can see that the chances that y will take the value 7 versus it will take the value 9 are again 2 to 3. The probability is 0.4, 0.6. So without any prior knowledge about x, or even if I will know that this is happening, x is 0, if I will know x is 1 or 2, if I will know x is 1, that is not changing absolutely the distribution of y. So that means that knowledge about x, or absence of that knowledge, is not changing, is not giving anything new to the distribution of y. That's why in this case y doesn't depend on x, and similarly x is not depending on y. You can consider, say, fix, what if I know that y is taking 7, the value 7? Then x will take these values with corresponding probabilities, or chances are 4 to 12 to 24. And what if y is taking 9? Then 6 to 18 to 36. And you can see that the distribution, that ratios are the same, in fact. Probabilities are the same of taking 0, 1, 2 for x. So x and y are independent in that case. Now we want to formalize that notion of independence. And we will formalize that, give the definition by using the ideas of independence of events. We have, in our first part of our course, we have considered the notion of independence of events. So just to recall that independence of events, let me give the definition. So events A and B are called independent if the probability of their intersection is the product of probabilities of A and B. So probability of A intersected with B is the product of probability of A and probability of B. Or in equivalent manner, we can define in the following way, in the case when probability of B is non-zero. So A and B are independent if the conditional probability of A given B is the probability of A. So the idea is that knowledge about the probability of happening one of A and B is not changing the probability of happening the other one. So if we knew that the event A has probability P without any prior knowledge, then after learning that B happened, we will still have the same probability P for A to happen. Let me give an example, just quick example. If I am rolling a die, so what is the probability that I will have 2? Fair die, I am rolling fair die. What is the probability that I will have 2? So the probability is 1 over 6, of course. But now think like this. This is calculation of the probability of 2 without any prior knowledge. I do not know any information. But now I have information, B is my information, that someone said that even number happened. So I know that only one of these 3 numbers can now be in the top face of my die. Now this is changing my probability of having 2. If I know already that only 2, 4, 6, one of these 3 numbers can happen, then the probability of having 2 now is 1 over 3. So this knowledge changes the probability of having that 2. In this case, we have dependence, of course. But if we have independence, that knowledge about B is not changing that prior probability we have calculated without any knowledge. Okay, this was from our first part of our course. Now we are defining independence of two random variables in a similar way. So assume X and Y are two random variables on the same experiment, on the same sample space. We will say that random variables X and Y are statistically independent or just independent, and we will write either by using this symbol or that symbol if the probability that X is in set A and Y is in set B is equal to the product of probabilities that X is in A and Y is in B. So probability that X is in A and Y is in B is equal to probability that X is in A times the probability that Y is in B. In other words, this means that these two events, X is in A and Y is in B, are independent. So X and Y, two random variables, are independent if for any sets A and B, these two events are independent. Or in an equivalent form, X and Y are independent if the conditional distribution that X is in A, given that Y is in B, is equal to the unconditional probability that X is in A for all A and B, such that the probability of having this is non-zero, is non-zero, to be able to calculate this conditional probability. Okay, so interpretation is the following. So having information about Y, say knowing that Y is in some interval, is not changing the distribution of Y, is not saying anything new about X. That is the notion of independence, idea of independence. Independence notion is symmetric. We will talk sometimes that X and Y are independent, or sometimes I will say that X is independent of Y, or I will say that Y is independent of X, and I will use that interchangeably. And if X and Y are not independent, then we say that they are dependent. And later we will talk about that linear dependency measure. As I have said, we will talk about covariance and correlation coefficient. I need to have double R here. Okay, so we have already defined it, that independence is, let me just quickly recall, we need to check that the probability that X is in A and Y is in B is equal to the probability that X is in A times the probability that Y is in B, and this needs to hold for any A, B in R, in fact measurable subsets of R. But we have infinitely many these kind of subsets, so practically checking independence by using this definition is not so nice, so practically impossible in fact, because we need to consider all cases of A and B. So fortunately we have another way to do that. So we can use the following equivalent forms for independence or descriptions of independence. So first one is in terms of CDF, and this method works for any random variables, continuous, discrete, even singular ones. So X and Y are independent if and only if their joint CDF is the product of marginal CDFs for any X and Y. So fxy, xy is the joint CDF for xy, for this pair. fxx is the marginal CDF for x, and this is the marginal CDF for y at the point y. So if we have this condition for any xy, then x and y are independent. If they are independent, I will go back. So if they are independent, then I will have this condition. Okay, the next one is describing independence of random variables through their PMFs in the discrete case. So assume x and y are discrete random variables, then x and y are independent if and only if their joint PMF is the product of individual or marginal PMFs. So the probability that x is taking the value xi and y is taking the value yj is equal to the probability that x is taking the value xi times the probability that y is taking the value yj. This needs to hold for any I and j, possible indices I and j. And if we have jointly continuous random variables, then the description or equivalent form for independence definition is the following. If x and y are jointly continuous, then x and y are independent if and only if their joint PDF is the product of marginal PDFs. So fxy small xy is the joint PDF of our random vector xy. fxx is the marginal PDF for x at the point x, and this is the marginal PDF for y at the point small y. And this needs to hold for any xy from R, for almost any x and y in R. If this holds, then x and y are independent. If they are independent, then this holds. In short, we can say the following. Independence means that their joint something is the product of individual something. Say joint CDF is the product of individual or marginal CDFs. Joint PDF is the product of marginal PDFs. Joint PMF is the product of marginal PMFs. Now, one property, if x and y are independent and we are transforming them separately, then the results are also independent. So this is the theorem, independence of transformations. Assume x and y are independent, and we have two functions, g and h, which are measurable functions. Then g of x, so I'm transforming this x, obtaining new random variable, and h of y are independent too. So example, x squared and cosine 2y plus 1 are independent if x and y are independent. Or sine of x and logarithm of 1 plus 1 over 1 plus y are independent if x and y are independent. Even we can write the following. Say h can be the same as g. So if x and y are independent, then x squared and y squared will be independent too, etc. So you can apply any function to g and any function to y, and you will obtain always independent new random variables. So this random variable and that random variable are independent. Okay, so let's move forward and talk about two types of problems we are solving, two directional problems we are solving when dealing with independence. So usually we deal with two types of problems concerning independence. So type 1 problems are the following. We know the joint distribution of x and y. So we have a lot of information about x and y. And we want to infer that x and y are independent or not, or dependent. Say we know the joint PDF, and we want to find whether x and y are independent or not. So what are we doing? We are doing the following. So we are calculating, we have the joint PDF, then we know how to calculate marginal PDF for x, marginal PDF for y, and we are checking if this condition is true for any x and y. If this is true, then we have independence. Otherwise, we do not have independence. Type 2 problems are of the following type. We know from the condition of the problem, from the very nature of x and y, that they are independent. And in that case, having that independent, we can construct the joint distribution of x and y from the distributions of individual distributions of x and y and solve problem concerning joint distribution. Say we can calculate this probability and the probability that xy is in some subset A. Say if we will know that x and y are independent, say from the very heart of our nature problem, or nature of our problem, or because it is stated explicitly in the problem that they are independent, and say if we will have individual PDFs of x and y, then using this condition, so in this case we have fxx, we have fyy, and we know that they are independent from the nature of our problem, so we will multiply that PDFs, marginal PDFs, to obtain joint PDF. And having that joint PDF, we will be able to calculate this kind of probabilities. Now let's separately talk about independence of discrete random variables, then for continuous case too. Assume x and y are discrete random variables with the following PMFs. So x is taking values x1, x2, etc. with probabilities p1, p2, etc. Y is taking values y1, y2, etc. with probabilities q1, q2, etc. Now x and y will be independent if and only if their joint PMF has the following form. So where is our joint PMF? Our joint PMF part is here. So probabilities are written here. So what we have, x is taking value x1, x2, etc. with probabilities. This is the marginal PMF for x. So x1 is taken with probability p1, x2 with probability p2, etc. Y is taking values y1, y2, etc. with probabilities q1, q2, etc. So I have marginal distributions written here and there for y and for x. Now x and y are independent if and only if each cell probability, say this probability, is obtained as a product of the corresponding probability for marginal of y and marginal of x. So this column and that row marginal probabilities product is at that cell. Say if I will consider this probability, so this is at this column and at that row, so q2 from here, p2 from here, and the product is written here. So if all elements in our joint PMF is obtained by multiplying corresponding marginal probabilities, then we have independence. And inversely, if we have independence, then all these numbers are obtained in that way. So let me erase this. So we have this table. So independence in the discrete case means to multiply that marginal probabilities, corresponding marginal probabilities. Now let's solve some problems. Assume x and y are discrete with the following PMFs. So x is taking these values with that probabilities, y is taking two values 10 and 20 with these probabilities. Are x and y independent or not? So you can think about that. But the answer is, well, we do not know, because we do not have the relationship between x and y. I do not know anything about their relationship. They can be dependent, they can be independent, that depends. So no information to make a conclusion. So this problem cannot be solved. Okay, so I'm changing something. Now I'm giving the same marginal or individual PMFs, and I'm saying that assume also that X and Y are independent. So now I'm giving that X and Y are independent. Having this, that, and independence, I can find the joint. So the first part is find the joint PMF of X and Y. Well, let me solve that. This is easy. So first I'm making that table. X, Y. X is taking values -2, 0, 1. And Y is taking values 10 and 20. Okay. And I know the marginal distributions, marginal PMFs. So let me try to fit it here. The marginal PMF for Y, I'm writing it here. So Y is equal to that particular value Y. Say for 10, it is 0.2 here. Y is taking the value 10 with probability 0.2 and 20 with probability 0.8. And X is taking its values with the following probabilities: 0.1, 0.6, and 0.3. And because I know that X and Y are independent, now I can fill this table. So here I will write the product of this and that. So 0.02. Here I will write the product of this and that, corresponding row and column marginal probabilities. I'm multiplying that. 0.12. So this with that, 0.06. Now this with that, 0.08. This with that, 0.48. And this with that, 0.24. Now I have the joint PMF for my pair XY. I have complete joint PMF. Now I can calculate any probability I want. Say probability that X times Y is less than 10. So I will check all possible cases to see which one is satisfying. Say -2 times 10. This is -20 and this is less than 10. So I will add this probability. Okay, 0, 10. I'm getting 0 here, so it is satisfying. So I'm marking that again. 1, 10. Well, 1 times 10 is 10. It is not satisfying this inequality, so I'm skipping this. Passing to that, -2 and 20. Well, -40, this is satisfying, so I will add this probability. Then 0, 20, 0 here, 0 is less than 10, so I will add this. And finally 120 is not satisfying, so I will not add. So the sum of these four numbers will give this probability. Okay. The next problem. Assume X is binomial with parameters 2 and 0.3 and Y is Poisson with parameter 2. And assume that X and Y are independent. Having individual distributions and their dependency, well, independence in fact, I can obtain the joint PMF. So I am giving by these three, I'm giving the joint PMF. So construct the distribution of XY. So find that joint PMF. I will do that. Okay, so let me construct that PMF table. Well, in fact, now I will take Y, the values of Y here. Well, because Y will have infinitely many values, I want to put them in a row. And X will take just few values, 3 values in fact. Okay, now I'm writing the values of X and the values of Y. X can take, because X is binomial with parameter 2, X is the number of successes in 2 trials. The number of successes can be 0, either 0 or 1 or 2 in that 2 trials. So 0, 1 or 2. Okay. Now the values of Y. y is Poisson, y can take the value 0, 1, 2, etc. etc. Okay. Now I need to fill this table, this infinite table, this joint PMF table probabilities. Okay, because I know the relationship between x and y, in fact I know that x and y are independent, I can fill this by using individual PMFs. So first let me write in this table, add to this table that marginal distribution. So in red, maybe I will add these probabilities. So probability that x is taking these values. So x is equal to that particular value x. Say. What is the probability that x will be 0? 0 means what is the probability that among that two trials no success happened. So no success happened, that means that two trials were failures, and the probability of failure is 0.7, so I will have this probability 0.7 squared because the trials are independent. Okay, what is the probability that x will be 1? X is 1, that means 1 success and 1 failure. Two cases, success, failure, or failure then success. The probability of success is 0.3, probability of failure is 0.7. So this is that probability. And x is 2 means both trials gave success to us, and the probability of that is 0.3 squared. Okay, now I have the marginal of x. Here I'm writing the marginal of y, or individual distribution of y, sorry. Let me erase this part maybe. And write y is equal, probability that y is equal to small y. The probability that y will be 0, because I know this distribution and I know that formula, is e to the minus lambda. Lambda is 2, so e to the minus 2 here. Here, the probability that y is taking the value 1 is e to the lambda times lambda to 1, so 2 to 1, over 1 factorial. Here, the probability that y will take the value 2 is e to the minus lambda times lambda to this power, lambda squared, over 2 factorial, etc. So I can write, in fact, for general k, the probability e to the minus lambda times lambda to k over k factorial. Okay, now I'm using this information to fill this table. This information says that corresponding, say, this probability is obtained by multiplying this and that. The corresponding row and some marginal product is written in this intersection of that row and column. Okay, so here I will have e to the minus 2 times 0.7 squared. This is times. Okay, here I need to write this times that. So e to the minus 2 times, well, 1 factorial is 1, times 2 times 0.7 squared. So e to the minus 2, well, this lambda is 2, in fact. Well, let me erase. Let me correct 2. 2 squared over 2, 4 over 2, again 2, times 0.7 squared, etc. Okay, here I will write the product of this and that. So e to the minus 2 times, well, 0.6 times 0.7. E to the minus 2 times 2 times this probability, which is, well, 0.42 in fact. So here I need to write this, e to the minus 2 times 2, if I will cancel 1 2's, then 0.42, etc. And here I will write the product of this and that. Say e to the minus 2 times 0.3 squared. Here I need to write the product of this and that. E to the minus 2 times 0.3 squared, e to the minus 2 times 0.3 squared, etc. So in this way I will fill my joint PMF. By the way, let me separate the joint PMF part. This is our joint PMF. This is our joint PMF. Well, maybe in this way. Okay. These are marginals just. Now we have solved this first part. The second part is saying find the probability that x plus y is less than 2. Having this table, having joint PMF, I can calculate any probability I want. So I am calculating that. I'm just finding all possible values of x and y satisfying this inequality. So x0, y0, I will have in the sum 0, this is satisfied. So I will add this probability. Then x is 1, y is 0. X is 1, y is 0. This sum is 1, it is satisfied. So I am adding this. X is 2, y is 0 is not satisfying because I will have 2, which is not less than 2, strictly less. So this is not satisfying. Y is 1, x is 0. So y is 1, x is 0. I am thinking about whether to add this or not. Y is 1, x is 0, sum is 1, this is satisfied, so I will take this. I will not take this because x and y are 1 for this case, and the sum is 2. So all others will not satisfy. In fact, only this 3 will satisfy. So this will be the sum of all these 3 numbers written here. And the C part is saying find the marginal PMFs of x and y. But of course we have calculated, we have started from marginal PMFs. So the marginal PMF of x will be this one, and the marginal PMF for y will be this one. You can check in fact in this way. If you will add all these numbers, you will get this. If you will add all these raw numbers, infinitely many numbers, then you will get this. If you will add these numbers, you will get that. And if you will add in this way, say if you will add these 3 numbers, you will get this. If you will add these 3 numbers, you will get this, etc. Well, this was a stupid question, of course, because we have started from marginals, from individual distributions to construct that joint PMF. Okay, the next one is the following. So assume we are rolling 2 dice independently. X is 0 if the first die is showing less than 3. 1 if it is showing 3, 4, 5. And 2, let me write the distribution first. So x is taking the following values. X is 0 if the first die is showing less than 3. That is, first die is showing either 1 or 2, and the probability of having 1 or 2 is 2 over 6. 6-sided die, and well, fair die, hopefully. And x is 1. So the next value of x is 1. If it is showing 3, 4, or 5, so 3 out of 6 values are giving 1. So 3 over 6. And x is equal to 2, x is 2, if the first die is showing 6. So the probability is 1 over 6. Only in the case when the die will show 6, I will have this. So the probability of that is 1 over 6. Y is taking 2 values, minus 10 and 12. So y is taking 2 values, minus 10 and 12. So in which case minus 10, if the second die is showing an odd number, and the probability of having odd number is 1 over 2. And here I will have 1 over 2, of course, because the sum needs to be 1. Okay, so construct the distribution of x and y. So let's look at the problem. Do we know other thing about x and y? So x is calculated from the throw of the first die. So x is from the throw of first die, and y is calculated from the second die result. So I'm rolling the dice independently. The result of the first die is not affecting the result of the second die. So it is natural to assume that this x and y are independent. So after having this, after assuming that x and y are independent, then I can construct the distribution of joint PMF of x and y. Very easy. Now the rest is like in that previous cases. So I'm writing possible values of x and y. So y can take two values, minus 10 and 12. And x can take three values, 0, 1, 2. I'm adding to this marginals. So marginal of y is here 0.5, 0.5. And here I'm adding the marginal of x. So marginal of x, marginal distribution of x, or marginal PDF of x, PMF, sorry, not PDF, PMF. 2 over 6, so 1 over 3, 1 over 2, and 1 over 6. Now I can fill my joint PMF table. This empty table is my joint PMF table. Say in other color, here I'm writing this times that. Because of this independence, I will write the products here. 1 over 3 times 1 over 2, 1 over 6, 1 over 4, 1 over 12. And here the same thing, 1 over 6, 1 over 4, 1 over 12. Well, you can check that these orange numbers sum up to 1. So this is legitimate PMF. Now having this, well, the problem is asking to calculate the probability that x times y is less than 10. So let me mark all probabilities I need to add. Well, x is 0, y is minus 10 is satisfying. So I will add this. 1 minus 10 satisfying. This is negative. 2 minus 10 minus 20, this is satisfying. So I'm taking this, adding this. 0, 12, this is satisfying. 1, 12 is not satisfying because I will have in the product 12, which is not less than 10, and 2, 12 is not satisfying. So I will add these 4 numbers to obtain this probability. And this is all. So from the heart of the problem, from the knowledge, from reading this problem, we have inferred that we have assumed that x and y are independent, and using that independent, we're able to complete this table and solve the problem. So another kind of problem, we have the joint. We want to infer, we want to check if x and y are independent or not. So assume the PMF of x and y is given through this table. X is taking these values, y is taking these values, and the joint probabilities are written in this table. So we want to see if x and y are independent. To that, what I'm doing, I'm first calculating marginals. So I'm calculating marginal distributions, marginal PMFs. So here I'm writing the sum. So this is marginal for y. Here I'm writing the sum 0.4. The sum of all these row probabilities I'm writing here. Here I'm writing the sum of this, so 0.2. And the sum of these 3 elements, 0.4. If I am doing that correctly, the sum needs to be 1. Okay, the other marginal, the marginal for x. So now column sums 0.1 plus 0.1 plus 0.2, 0.4 here, 0.3 here, and 0.3 here. Again, this sum need to be 1, and it is giving 1, so this is correct. Okay, now how to check that x and y are independent? I need to check if all elements are obtained by multiplying the corresponding row and some marginal probabilities. Say this, I need to check if this is obtained by multiplying this with that. Of course, it is not correct. Well, in the case of independence, I need to have 0.16 here, not 0.1. So already this is saying that we do not have independence. By the way, this we could start from this 0. Let me erase. Well, if we have 0, if they are independent, say I have Q here, Q2 and P2 here, then I need to have that either P2 is, if they are independent in fact, then I need to have that 0 is equal to Q2 times P2. So either Q2 is 0 or P2 is 0. If Q2 is 0, then this row needs to be all zeros. If P2 is 0, then this column needs to be all zeros. But because we do not have that properties, then this shows that x and y are dependent. So x and y given through this table, through this joint PMF, are dependent random variables. Now the next one with the same values for x and y, but with other probabilities. Let me check if these random variables x and y are dependent or independent. So I'm calculating marginal distributions, marginal PMFs. So for y is equal to y. I'm adding these 3 probabilities in a row to write it here. 0.20, 14, 0.2 here, 0.2, 28, 0.4 here, and I need to have 0.4, another 0.4 here. Let me check. Yeah, the same is written here, so 0.4 here. Okay, now I am adding the marginal distribution of x, so PMF for x. Now I am adding column wise, so the sum of all these elements will be 48, 0.6. Here I need to have 0.1, and here 24, 0.3. Yeah, the sum is giving 1, so this is correct. Okay, so now let me check if x and y are independent or not. How to check? I need to check the following. Every element in the joint needs to be obtained, in the case of independence, need to be obtained from by multiplying the corresponding row and some marginal probabilities. So 0.6 times 0.2 is giving 0.12. So this is okay. 0.2 times 0.1, 0.02. So this is okay too. 0.3, 0.2, this is okay too. So you can check every element in this joint PMF that it is obtained by multiplying corresponding probabilities. Say 0.04 is obtained by multiplying 0.1 and 0.04. So we have obtained 0.04. Okay, so in this case, x and y are independent. So how to check independence again? First calculate marginals, then check if every element is the product of corresponding row and some marginal probabilities. Okay, let's move forward. Assume I am picking a random, assume I am picking at random 2 numbers from 1, 2, 3, 4 uniformly independently. So 2 numbers out of this independently. let max be the maximum of that numbers and mean be the minimum of that numbers. So I will have two numbers. Say first time I'm choosing 3, second time I'm choosing 1, then maximum is 3, minimum is 1. Okay. In general, maximum and minimum will be random numbers, because before doing that experiment, before picking two numbers independently, I will not know the values of max and min, so they are random variables. So, and the problem is asking, are max and min independent or not? So to check that, I need to construct joint PMF for max and min to solve this problem. So let me do that. Max, the values of max, the values of min, and the variable min. So because I'm choosing elements from 1, 2, 3, 4, max can be maximum of, I'm choosing two elements. Say the first time I'm choosing 1, second time I'm choosing 4, then the maximum is 4. The maximum can be either 1 or 2 or 3 or 4. And the minimum also can be one of these four numbers. 1, 2, 3, or 4. Well, this is 3 or 4. Okay. Now I need to fill this table, then check if maximum and minimum are independent. First, let us fill this table. So what is this probability? So what is saying this? To calculate this probability, I need to calculate the probability that maximum is 1 and the minimum is 1. So that can happen only if I am picking, first time I am picking 1 and the second time I am also picking 1. If I will take any other value for one of the cases, say for the first number I will pick, say 3, the maximum will be 3. Say. So maximum and minimum are 1 only in the case when the two numbers are the same, and the probability of having 1, 1 is 1 over 16. Because I am choosing two times independently a number from 1 to 4. Each time the probability of choosing particular number. So the first time, the probability of choosing first time this 1 is 1 over 4. And the second one, second times choosing 1 is again with probability 1 over 4, so 1 over 16. Okay, so what about this? Minimum will be 1, maximum is 2. In which cases I will have minimum is 1, maximum is 2. So I'm picking two numbers, minimum is 1, maximum is 2. That can be in two cases. Either I'm picking in this order, 1, 2, or 2, 1. Minimum is 1, maximum is 2. So I will have the probability of choosing this 1 over 16. The probability of choosing this is 1 over 16. So I will have 2 over 16. Now this. What is the probability that maximum is 3, minimum is 1? That can happen only in these two cases. Either I'm picking 1, 3 or 3, 1. And the probability of that is 2 over 16. Similarly, this is 2 over 16. Now let's think about this. What is the probability that maximum is 1 and the minimum is 2? Well, if maximum is 1, minimum cannot be 2. Maximum will be less than minimum. That is not correct, of course. So the probability of that is 0. And of course the probabilities here are also 0. Maximum is 1, minimum cannot be 4. Maximum is 2, minimum is 2. So I'm filling this. Maximum is 2, minimum is 2 can happen only if I am picking this pair. The first time I'm picking 2 and the second time I'm picking again 2. And the probability of that is 1 over 16. Okay, I cannot have maximum is 2 and minimum is 3. So here I need to write 0 and 0 here. Now this number, so maximum is 3 and minimum is 2. Means I will have 2, 3, so minimum is 2, maximum is 3, or 3, 2, minimum is 2, maximum is 3. And two cases, and probability is 2 over 16. Here again I will have 2 over 16. Either I will have 2, 4 or 4, 2. Okay, this case is 3, 3. Maximum is 3, minimum is 3. That can happen only in the case 3, 3, and the probability is 1 over 16. Here I will have 2 over 16. Here I will have 1 over 16. Here I will have 0 because I cannot have maximum is 3, but minimum is 4. Okay, this is our joint PMF constructed from the problem. Now I want to check if max and min are independent. To that end, I need to construct joint. Sorry, not joint. We have already obtained that joint. I need to construct marginal PMFs. So marginal PMF. Let me erase this part. Marginal PMF for minimum. This random variable min. The min is equal to that particular value 1, 2, 3, 4. I'm adding all these numbers. Sorry. So 2, 2, 2, 6, 7, 7 over 16. I'm adding these 4 numbers. 2, 2, 1, 5 over 16. Here I am adding all these numbers and I'm obtaining 3 over 16 and 1 over 16. 16. Something is wrong. Let me erase. Write it again. So 1 over 16. Yeah. Now I need to add the marginal for max. Max is taking the particular value 1, 2, 3, 4. Here I need to add all these elements in a column, 4 elements in a column, 1 over 16. Here I need to add these column elements, 3 over 16. Here I'm adding these 3 elements, in fact 4, but this is 0, 5 over 16, and 7 over 16. These are marginal PMFs. Now, to check that independence, I need to obtain that every element here, say this element, is obtained by multiplying this by that. Well, of course, this is not correct. And even more, we have zeros here, but we do not have zeros in the marginal. So we cannot obtain 0 by multiplying non-zero elements. So they are not independent. So max and min are dependent. Okay. Now let's talk about the independence of continuous random variables and start by solving straightforwardly problems. So assume x is uniform in 0, 1 and y is uniform in 2, 4. Are x and y independent? Well, again, we cannot say anything because I have individual distribution of x, I have individual distribution of y, but I do not know the relationship. Maybe they are independent or maybe they are dependent. I do not know. So, not enough data to answer to this question. Another one, x and y are normal with 0, 1, so they are identically distributed, standard normals. Are x and y independent? Again, the same answer. So, no information to conclude. I do not know. I have individual distribution of x. I know individual distribution of y. Maybe y is equal to exactly x. Maybe y is equal to minus x. Maybe y is defined on completely other experiment. Maybe y is defined on the same experiment as x, but they are independent, etc. So nothing can be said about the relationship of x and y, knowing only individual distributions, even if that distributions are the same. Even in that case, we do not have just the relationship between x and y, the dependency. So I cannot say anything for this problem. Now, assume x and y joint, we are given the joint PDF in this case. So it is uniform in T, where T is the triangle with these vertices. Are x and y independent? So the method is the following. I am writing from this the joint PDF. Then I am calculating marginal PDFs. Then I am checking if joint PDF is equal to product of marginal PDFs at any point. If that holds, then they are independent. Now let's do that gradually, step by step. So T, first I am drawing that T. This is X, this is Y. T is with vertices at 0, 0, 0, 1 and 1, 0. So let me first join by a line. Okay, this is 1, this is 1. So this is my T. This is T. And this line equation is y is equal to 1 minus x. So this line equation is 1 minus x. Okay, now first I'm writing the joint PDF, because I know that joint PDF, the distribution is given. So joint PDF is, by the definition of uniform, 1 over the array of T, and the array of T is 1 times 1 times 1 over 2, so 1 over 2, 1 over 1 over 2, so I will have 2 here, if x, y is in that triangle and 0 otherwise. So let me erase and write 2 here, so I'm erasing this and writing just 2, 2. This is joint PDF. Now I need to calculate marginal PDFs for x and y. So marginal PDF of x is the integral from minus infinity to plus infinity of the joint dy. So I am integrating out from this joint PDF the other variable. Okay, so let's see what is happening here. I will have several cases. If my x is here, I'm integrating over y. That is, I'm integrating over this line from minus infinity to plus infinity. I'm moving over this line and integrating over that. And because here my joint PDF is 0, the integral will be 0. So I will obtain the following. 0 if x is not in 0, 1. So if my x will be here, again I am integrating 0 function, so I will get 0. So if x is not in 0, 1. What will happen if x is here, between 0 and 1? This is 0. Then I am integrating, in fact, over this segment from this point to that point. Because on the other parts of this line, my f is 0. F is non-zero only in this triangle. Okay, so I'm integrating from 0 to this point, and this point is y is equal to 1 minus x, so 1 minus x. And the value of my joint PDF, is 2 here in the triangle, so 2 dy. Y is changing from 0 to 1 minus x, this height. And this integral is for x between 0 and 1. Now if I will calculate this, I will obtain 0 if x is not in 0, 1, and 2 times the length of this interval, or 2 times 1 minus x, if x is between 0 and 1. This is the marginal for x. And because of symmetry of my domain and my function with respect to x and y, if I will change the places of x and y, if I will write y here, x here, the picture will remain the same, exactly the same. So I will have fy at y is given to the same function. Well, if I am writing with respect to y, I need to change to y. If y is between 0 and 1, and 0 otherwise, if y is not in 0, 1. Now I have both marginal distributions and I have joint distributions. So let me check if joint is the product of marginals or not. If I will erase this part, I'm writing that equation to check. So what I will write, I'm checking if fxy is equal to fxx times fyy, for any x and y. So so I need to check, say, well, in fact, this is not correct for any x and y, because in some region, well, in fact, the product fxx times fyy will have the following form. So this is equal to this times that, so 4 times 1 minus x, 1 minus y, if x and y are between 0 and 1. And otherwise it is 0. 0 otherwise. So even the range where f is 0 is not coinciding with the range where this product is 0. Say this product is non-zero in the square 0, 1, 0, 1. So this is where my product is non-zero and my joint PDF is non-zero only in the part of this, in the triangle, in this triangle. It is non-zero in this triangle. So joint is not equal to this product for any point, for any x and y. So that means that they are not independent. They are dependent. Okay. Let's move forward. So the next one is the following. Again, uniform distribution, but in a circle, in a unit disk, in fact. So first, geometrically, the domain where we are doing our calculations, where our random variable is uniformly distributed. Okay, so this is 1, this is 1. This is our domain. Now, what I need to do, first I'm writing, we need to check if x and y are independent. So what we have x and y are uniformly, this random vector is uniformly distributed in D, and we need to check if its coordinates x and y are independent or not. So first I am writing the joint PDF, then I will calculate marginal PDFs, then I will check if joint is the product for the product of marginal PDFs for any x and y. So the joint is given through this formula. This is from the definition of uniform distribution. 1 over the area of that D, in our case the area of this circle, and that will give pi, 1 over pi, the area, if xy is in D and 0 otherwise. Now, next I'm calculating the marginal of x. So I'm integrating again from minus infinity to plus infinity fxy dy, integrating out the other coordinate y. So I want to have the coordinate x for my distribution of x. Okay, so again I need to consider cases if this is minus 1, this is 1, and this is minus 1. If my x is here and I'm integrating over this line, or my x is here and integrating over this line, I will have that integral is 0, because my f, this is the support of f. Outside of this region, this f will be 0. Say at this line it will be 0, at this line it will be 0. So this is 0 if x is not in minus 1, 1. And it is, if x is between that minus 1 and 1, let's see what is happening if x is here. If x is here, I need to integrate from this point to that point. So how to find that points equations? I'm taking the equation for this. This is x squared plus y squared is equal to 1. And I'm solving for y, to find y, to find the height. So either y is equal to, from this y squared is 1 minus x squared, so I will have plus or minus 1 minus x squared. So the upper part of this circle corresponds to the positive square root sign, and the lower part corresponds to negative square root of 1 minus x squared. So this point will be y is equal to minus square root of 1 minus x squared. And this point corresponds to plus square root of y is equal to square root of 1 minus x squared. Now I am integrating over this line, so I'm integrating over this segment from minus square root of 1 minus x squared to square root of 1 minus x squared. And I'm integrating f, and f is 1 over pi dy. This goes out, I'm integrating 1, so I will have the length. The length is this minus that, and I will have 2 pi. 2 is from this minus that, it will give 2 times this square root. Square root of 1 minus x squared. So this is the marginal PDF for x in the case when x is between minus 1 and 1. Now, because of the symmetry of this region around x and y in terms of x and y, and because of symmetry of our function f, so this function is symmetric about x and y, so in terms of x and y, if I will change the names of x and y, then nothing will happen with my function, it will be the same. So I will have that fy is exactly the same, is given exactly by the same formula. So I will have 0 if y is not in minus 1, 1. And I will have 2 over pi square root of 1 minus y squared if y is between minus 1 and 1. Now I need to check the independence. I need to check whether f is equal to this product or not. Let me write that product to see if it is giving 1 over pi over d or not. I will erase this part. I need a space to write. So what I'm doing, I'm calculating this product. The product of marginal PDFs is equal to the following. So I will have non-zero only in the case when y is here and x is here, and in that case I will multiply these two numbers, and I will have 4 over pi squared times square root of 1 minus x squared times 1 minus y squared if x and y are in minus 1, 1. And 0 otherwise, because I will have one of the terms is 0, then product will be 0. Now you can see that even the supports of these two functions are not the same. So for this and this, so support are not the same. The support of product of marginals is minus 1, 1, minus 1, 1, minus 1, 1 is the square. f is non-zero here. F is given through this formula here, and f is 0, not f, sorry. This product is equal to this quantity inside this square, and it is 0 outside of that square. And what about that joint PDF? It is non-zero in this circle, so it is non-zero here, and 0 otherwise. So it is this joint PDF is 0 here, 0 here, 0 here, 0 here, but this product is not 0 there. So this cannot be equal to that for any x and y. So x and y are dependent in this case, not independent. Okay. The next one is the following. Almost the same problem, I'm changing the domain. This point xy is uniformly distributed in D, where D is this rectangle now. Are x and y independent? In this case, we will have independence, so let us check. So I am starting again from picture, the support of our joint PDF. D is -2, 2, and 0, 1. Say this is 1. I will have this portion, this rectangle. So this is the joint PDF will be the following: 1 over the array of this. So height is 1, width is 4. So I will have 4, 1 over 4. If xy is in that D rectangle, 0 otherwise. Now, having this, I need to calculate marginals. Marginal for x, say. So I'm integrating over -infinity to +infinity our joint PDF dy with respect to y. Again, two cases. If x is outside of this interval -2, 2, this is x. I'm integrating over this line. I'm getting 0 because f is 0 there. 0 if x is not in -2, 2. And what will happen if my x is here? If x is here, I'm integrating over this line, so I'm integrating only over this segment, because outside of that f will be 0. And this segment is, y is changing from 0 to 1. This is 1. So I am always integrating from 0 to 1. My joint PDF, our joint PDF here is 1 over 4, so 1 over 4 dy. And this is equal to 1 over 4 exactly, if x is in -2, 2. So I have obtained that marginal for x. Now I need to calculate the marginal for y at the point y. Now my domain is not symmetric anymore with respect to x and y. If I will change the names of x and y, I will not have the same picture. If this will be my x, this will be my y, I will have this kind of rectangle now, not the same rectangle. You can try to change these names by y and x to understand that what is the picture in this coordinate system for the, if I will change the names of x and y, places of x and y. Okay, so I need to calculate this separately. I am integrating out from the joint PDF. This is +infinity. The variable x now, f x y dx. Okay, So fixing y, I'm fixing y, integrating over x, that is integrating over these horizontal lines. Now I'm considering again cases. If x is here, not x is here, sorry. If y is here, we are fixing now y. If y is here, then I'm integrating over x over this line, my joint PDF, which is 0. So if y is here, this is y over there, then integral will be 0 again. So this is 0 if y is not in 0, 1. And what will happen if y is between 0 and 1? Y is here. So I'm integrating over this line. In fact, I'm integrating over this segment up to this point. From this point to this point. And that is, I'm integrating from -2 to 2, -2 to 2. I'm integrating this function, which is 1 over 4 dx, in this case dx, and which will be 1 over 4 goes out, and I will have the integral of 1 from -2 to 2, that is giving the length of this interval, which is 4. So 4 over 4, 1. If y is from 0 to 1. By the way, the distribution of fx and fy is uniform. Say fy will be uniform in 0, 1, and not fy. Y itself is uniform in 0, 1. This is what we have obtained. We have shown that the PDF of y is 0 if y is not in 0, 1, and 1 is 1 in this interval 0, 1. Okay, and for x I could say that x is uniform. This is not important, but let me write not important in this for this problem. So uniform from -2 to 2. So x is uniform from -2 to 2, and y is uniform from 0 to 1 in this case. Now I need to check if the product of marginals is giving exactly the joint. So let's see that it is giving in this case. So I'm calculating here, somewhere here, the product of marginals. Okay, so this is giving. This is my one marginal, and that is one marginal. I will have either 0 if I will multiply 0 by this, or 0 by that, or 0 by that. And non-zero will be if I will multiply this by that. So 1 over 4, and in which case that will happen if y is from 0, 1 and x is from -2 to 2. So x is from -2 to 2 and y is in 0, 1 and 0 otherwise. Now you can see that this exactly coincides with that. Well, this region D is -2, 2 times 1, 0, 1. So this is exactly this. For any point x, y. So in that case, we will have independence. So the result, the answer is that x and y are independent in this case. Okay. Let's move forward. Assume x and y are height and weight of randomly chosen person. Are x and y independent? Well, in fact, to solve this theoretically, I need to have the exact distribution of x, y, the joint distribution of that random vector x, y. But nobody will give me that distribution of height and weight, all heights and weights of every person. But we can just have a look at some data sets. Say this is from one of our last lectures. This is, let me just open, from Penn State, Abel College of Science, elementary statistics course, and some data sets. Baseball, not interesting to us. Example, height and weight. Data concerning body measurements from 507 individuals. So this is the picture of a dependence of height and weight. So scatter plot of weight versus height. So what this shows, say, if I would take any value, so what this shows, say, this shows height and weight for some person. So some particular value for our random vector HW, height, weight. So this is for another person. So that person's height was almost 190 and the weight was this much. This is for another person. So 507 points, possible values for our random pair HW. But you can see from this that there is a tendency, there is a relationship between X and Y. If X is increasing, say if X is here, then Y is more or less higher. So Y tends to increase too. So if we are moving this way, so if I am decreasing X, then that decreases also Y. Y is also decreasing in general. Well, not for all cases, but in general, I can say that it is decreasing. So X and Y, height and weight, are dependent from this picture. In fact, in statistics course, you will learn how to model the linear relationship. So this will be linear regression line. So best fit line to this cloud of points. So, and you can see that there is a trend almost with this linear relationship. If weight is increasing, if height is increasing, then the weight is increasing almost like this relationship. Okay. So this much about that problem. Let's go back to our slides. This is not our slides. Okay. Where are my slides? Yeah. So assume X is uniform in 0, 3, Y is exponential 2, and assume now we know that X and Y are independent. So this is type 2, second type problems where I have marginal distributions, individual distributions, and I have that they are independent. So from this I will obtain the joint PDF and I will be able to calculate probabilities. Okay, the first part is saying find this probability that absolute value of X plus absolute value of Y is less or equal than 1. In fact, because X is uniform from 0 to 3, X is taking values from 0 to 3, X is positive, non-negative. Y is exponential, it is non-negative, so I could just skip that, but okay, I'm writing in this way. So what I'm doing, I'm starting from individual PDFs first to solve. So for X, this is 1/3, the PDF of uniform, if X is between 0 and 3, and 0 otherwise. For Y, the PDF is the following. So PDF of exponential, 2 times lambda times e to the minus lambda x, so 2x, not x but y, our variable is y, if y is larger or equal than 0 and 0 otherwise. Now, since x and y are independent, then I will obtain the joint. So X and Y are independent. So this is joint PDF is the product of individual PDFs, the marginal PDFs. So this will give the following values. 1/3 times this, that is 2/3 times e to the minus 2y, if X is between 0, 3, and if Y is non-negative, otherwise it is 0, because I will have one of the terms is 0 in the product, otherwise. So I have the joint. Now I can calculate that probabilities. First, let me erase and draw that graph. So erase this part. And now I will calculate that and then simulate in R to calculate that probabilities. Okay. So geometrically, we have the following picture. This is X, this is Y. I want to draw the support where our joint PDF is non-zero. X is moving from 0 to 3. And Y is non-negative, so Y is above this line. And I will have the following half strip. So here, in this region, our F joint PDF is given by this formula. Otherwise, our joint PDF is 0. Okay. Now we are asked to calculate the probability that absolute value of X plus absolute value of Y is less or equal than 1. That will be this kind of region. Well, if we will take 1 here, 1 here, square with side square root of 2, in fact. But this is not important because we need to intersect with the support. So we will have just this region for integration. So if we will denote that by A, this solid, mark it triangle by A, then probability that this probability will be double integral over that A of our joint PDF. So I'm integrating that joint fxy dx dy. So it remains to write in the iterated integral form to calculate this integral. So x is in this region, in this A, x is moving from 0 to 1. X is from 0 to 1 dx. And for each x, if I will fix x here, then y is moving from 0 to this line equation, and again we have 1 minus x. Y is equal to 1 minus x for the equation. And we are integrating for this fixed x, y is changing from 0 to this height. Y is from 0 to this height. From 0 to 1 minus x. And I need to plug f. F is 2 over 3 e to the minus 2y dy. So I need to calculate this probability. Let's calculate and see what is happening here. So I'm keeping the outer integral. I can take that 2 over 3 out. Okay, I will write it 2 over 3 dx. And now I have e to the minus 2y dy. Then if I will write minus 1 over 2 e to the minus 2 y, then this is the antiderivative of that. So if I will calculate the derivative of this, the derivative of this will be, this is constant, this goes out, e to the minus 2y, the derivative of this will be the same function, e to the minus 2y, times the derivative of the power, and that will give minus 2, will be cancelled with this, I will be left with that. So the integral of this is this. And I'm plugging y is equal to from 0 to y is equal to 1 minus x. So if I will plug, I will obtain 2 over 3. This is 2 over 3. Integral from 0 to 1. Now I'm plugging this value. Well, let me take this out. If I will take this out, I will have minus sign 1 over 3. 2's will be cancelled, this one minus sign. Okay, and here I'm plugging this value. I will have e to the minus 2 plus 2x. Plus 2x. and minus 1. So this kind of thing, dx. I'm erasing this part because we have already used this. I can erase this to have a space to solve. This is equal to. Why I am doing calculations? Because I want to have the final answer to check with R if I am calculating that correctly. So I had minus sign here, so I can change the places. I will have 1 over 3 integral from 0 to 1 1 minus e to the minus 2, I'm separating that, times e to the 2x dx. So if I will calculate separately the integrals, 1 over 3, the integral of 1 is 1 from 0 to 1. So I will have 1 minus, this goes out, e to the minus 2. And I need to write the integral of this. The integral of that will be 1 over 2 times e to 2x. And I need to plug here, well, here I need to plug. Well, let me erase this last thing, because I'm plugging not here but for this. X is changing from 0 to 1. From 0 to 1. I'm integrating this part, I'm obtaining this. I have already integrated this. The integral of 1 from 0 to 1 was the length of this integral, length of that interval, and that was 1. Okay, so let me plug the values. 1 over 3, 1 minus, I'm plugging 1, e to the minus 2. What I'm obtaining, e to the minus 2 over 2 times e to the 2, something like this. And minus or plus, because we had that minus sign, e to the minus 2 over 2 times 1. So this will be enough. Okay, this is enough. I will have these two cancelled. 1 minus 1 over 2 will give 1 over 2. I can take this 1 over 2 out of this parentheses. I will have 1 over 6. So instead of this I'm erasing, I'm writing just 1 over 2. Taking out that 1 over 2, I will have 1 plus e to the minus 2. So this is the result. This is that probability we have calculated. 1 over 6 times 1 plus e to the minus 2. Okay, so the part B is saying calculate the same probability by using Monte Carlo method simulations in R. So x is uniform in 0, 3, y is exponential with parameter 2. And I know that x and y are independent, so I want to calculate this probability that x squared, not x squared, the absolute value of x plus absolute value of y is less or equal than 1. So how I am doing that? First erasing this. Now I will generate random numbers from uniform. Then independently random numbers from exponential 2. Let's do that. So first number of elements, say number of points I will generate. Say we are starting from 1000. Now generating uniform numbers RUnif, and from 0 to 3. That was from 0 to 3. Next, y is Rx exponential, and points give me endpoints with rate 2. The parameter was 2. By the way, because I am running these two lines, separately, then x, the values of x and the values of y will be independent in this case. So when running this, then running that, it is giving independent in some sense. Independent, of course, statistical, in statistical sense, independent numbers. Well, obtaining dependent numbers are much harder than independent numbers in R. So if I will give some particular case of dependence and ask you plot this kind of numbers, that will be not so easy. But if you are running this separately with separate lines, you are getting independent things. Even if I will write x is R unif and y is R unif from the same distribution, then that point x and y will be in some sense independent. Okay, so I'm obtaining that x and y. Now what I need to do, let me do the following. My aim was to calculate probability that absolute value of x plus the absolute value of y was less or equal than 1. So what I will do, if I will run this, that will give false or true if some point xi, yi, so x is vector of size 1000, y is vector of size 1000. So it is checking x absolute value of this plus absolute value of that is less or equal than 1. It is printing true, otherwise false. So think like this. I am dropping a lot of points and I want to calculate how many of them are in the region. I'm dropping points inside that strip, half strip, red region, and I want to calculate how many of that points are in that region, the probability of which we want to calculate. Now I need to find how many points I have. I have falses and trues. To calculate that number of elements that are satisfying this inequality, I'm just summing that trues and false. Because false is 0 and true is 1, so I will have sum of truths, sum of points that are inside that region. And if I will divide that by the total number of elements I am choosing, then I will get some approximation for my probability. Let me check, say how I am checking. Let me print actual probability. That actual probability was, well, 1/6 times, let me first write 1 plus exponent to minus 2, that was exponent to minus 2 over 6. If I remember correctly, this was the value. And the value of p is 1.89, and we have obtained 0.191. You can see that this is very close. If I will increase this, say 10,000, run that again, well, this is the actual, this is what I have obtained. If I will run that again, say, okay, 9.2. Let me show how we can see if increasing n will give more and more close approximation to that number. So I want to do the following. I want to change that number n. I want to increase that number n. For each number n, I want to do this calculation and print that probability obtained versus that n. Say for 10,000, I will print that probability 0.192 or something, which will be generated later, because every time if I will run that code, I will get different numbers, close to each other, of course, but close to but different numbers. Okay, so what I want to do, I am running. This is maybe not the most effective way, but I am writing a loop. K is running, K in, so I need to write in this way. 1 to say 1,000 or maybe 5,000. For each K, I'm doing the following. I'm taking n to be, I will not do calculation for any K from 1 to 5,000. For that case, I will not calculate this probability by using this formula, but I will do that calculation for 10 times k. So I'm taking n is equal to 10 times k. Okay. Well, k is not found. That's correct, because I need to run the whole loop. I will not run that yet. So I want to write the following. I want to keep n, the n's, because later I will draw the graph of possible values of n and obtain its probabilities. So n values, say n vals. I'm taking a empty vector, and every time I will obtain n, I am adding to that empty vector that new n. So I will have, in fact, n is equal to 10, then 20, then 30, etc., up to 50,000. Well, I can do that, of course, in other ways, but I am writing in this way. That's okay. So n vals, I'm updating that n vals. I'm concatenating that n with n vals. Okay. Now, what next? For each n, I am generating x and y. So for each n, I will generate x and y. I will calculate this probability. How many points are inside that region over total number of points taken. I am denoting this by, say, p approximated. Say approximated is this much, and then I'm keeping this in a vector later to print that. So p vals is first empty vector. I'm running this, and here every time I will obtain new value, this value, I am keeping in that vector. So p vals, I'm updating that p vals. This is, I'm concatenating the old p vals with p approximated, that new value. Okay. If I will run this loop, so let me run that. See if that is running. Yeah, that is calculating. Okay. That will take a time a little bit. Now, after having that p-vals, what I want to do, yeah, I have already that values. So I want to plot n vals versus n vals versus p vals, or p vals versus n vals, maybe that's correct. Join with lines. Okay. L is not, yeah. I need to write in this way. And run that again. Well, this kind of, yeah, picture. See what is happening. Well, something is not correct. Maybe what I'm doing wrong. If I will take, say, some small number, say 1,000, run that. Okay. Okay, so I need to run from this. Yeah. I'm doing the following. Not correct. I'm not correctly adding in the order is not so correct. So p-vals I'm adding in the following order. First I'm writing n, then n-vals, the old, so 1, then yeah, so I need to add in this order, so order matters. The new value after the old ones. So let me start from this, that. Yeah, now everything is okay. Then I want to add to this the actual probability. The actual probability was that p calculated. I'm not change it. I have not changed that. So there is a command AB line that can add without erasing this plot a line. If I will write horizontal h is equal to p, that will take a horizontal line passing through y is equal to p, and line with this, say 2, a little bit thick line, and color is in red. Yeah, red. And you can see that my if n-vals is increasing, then that calculated probability p-vals are getting closer and closer to that actual real value. Okay, even I can make this 2000 and run everything again. So try to see if that is working well. Yeah. So I have approximation to that actual value. So by just having simulations, I can calculate that probability. In fact, this Monte Carlo simulation is giving a tool to calculate integrals, and very complicated integrals, by just using probabilistic tools and simulations like this. Okay, let's move back to our problem. So the next one is, assume that the lifetime of a desktop computer, HDD, is exponentially distributed with parameter 0.2 random variable, and the lifetime of CPU is exponential 0.1 distributed random variable in years. So the average year for CPU is 1 over 0.1, 10 years, and 5 years here for the hard disk, say, HDD. Assume that lifetimes are independent. Well, we can assume that the lifetime of hard disk is independent of the lifetime of CPU. Okay, what is the probability that computer HDD and CPU will work more than 3 years? So what I want to calculate, so HDD or H is the lifetime, say H is the lifetime of hard disk, C is the lifetime of CPU, so H is exponential with 0.2, and C is exponential with parameter 0.1, and H and C are independent. So this is given. What's the probability? I'm solving the A part. What is the probability that computer HDD, hard disk, and CPU will work more than 3 years? So H is larger than 3 and C is larger than 3. Because of independence, I can write this is H is larger than 3 and times probability that C is larger than 3. CPU lifetime is larger than 3. Now, because I have this distribution exponential 0.2, I can calculate the probability that H will be larger than 3. Then having this, I will calculate that, multiply to obtain that. Let me just recall how to calculate this. H is larger than 3. This is 1 minus, for exponential I am using CDF. So 1 minus the value of PDF for H at 0.3, and that CDF value was 1 minus e to the minus lambda times that x. Lambda is 0.2 and x is 3. So I will have e to the minus 0.6. So this is e to the minus 0.6. In a similar way, I can calculate this and multiply to obtain the requested probability. Now for the B part, so erasing this. For the B part, I have the following. What is the probability that either computer hard disk or CPU will work more than 3 years? So I'm asked to calculate probability that H is larger than 3 or C is larger than 3. Well, I can use that union formula, so probability of this plus probability of this minus probability of intersection, and we have calculated in the previous problem that probabilities, or maybe we can do that second solution is geometrically. H and C are exponential, so if this is H, this is C, I will have just in this region, H and C are both non-negative, so they are in this region. So this region, the requested region, the probability of which we are calculating is the following. H is larger than 3, so H is larger than 3 is this region, or C is larger than 3. This is 3, C is larger than 3 means this region. And we need to intersect with our support. So this will be the requested part. We need to integrate our joint PDF over this, or which is the same, we can calculate 1 minus the probability that HC is here. So this is equal to 1 minus the probability that H is less than 3 and C is less than 3. And because of independence, I can write 1 minus probability that H is less than 3 times the probability that C is less than 3. And we can calculate these probabilities easily, like in our previous case, part A, and multiply them, and then 1 minus, calculate 1 minus the product of them. Okay, this much about this problem. So a little bit about independence of more than 2 random variables. This is important because in statistics, and because this is important not only for statistics, it is very important in statistics, but also for limit theorems we will learn at the end of our course. For central limit theorem and law of large numbers, we will consider n independent random variables. So we need to know what independence for n random variables means. So like in the case of events, we are defining 2 notions of independence for n random variables: pairwise independence and mutual independence, or just independence. We say that x1, xn, random variables x1 to xn, are pairwise independent if for any I and j different, xi and xj are independent. So any pair of random variables is independent. And we say that this collection or these random variables are mutually independent, or later if we will talk about n random variables and we will say they are independent, we will mean mutual independence, this independence. So x1 to xn are independent if for any subset ak in R, the probability that x1 is in A1, x2 is in A2, etc., xn is in An, can be calculated as a product of these individual probabilities. So probability that x1 is in A1 times the probability that x2 is in A2, etc. So this is straightforward generalization for the 2-dimensional case, independence of 2 random variables. And important note, mutual independence, this independence implies pairwise independence, but the inverse is not true. Inverse implication is not correct. Say how to prove that this independence, mutual independence implies pairwise independence. Say if I want to show that x1 and x2 are independent, then I can take, say, A3 to be R, A4 to be R, etc., AN to be R. If I will take, say, all others to be R, then this condition, x1 is in A1 and x2 is in A2 and x3 is in A3, but x3 is in A3, every point will satisfy, no need to write that. x4 is in A4, A4 is R, so x4 always will be in R, so no need to write that. So I will have just here probability that x1 is in A1 and x2 is in A2. If I will take A3, A4, all others to be R. Here I will obtain probability that x1 is in A1 times probability that x2 is in A2. Next is probability that x3 is in A3. But x3 is in A3 gives omega. All points are satisfying and the probability of that is 1. So I will have just this equality, which means this will hold for all A1, A2, which means that x1 and x2 are independent. Okay. So later in statistics, we'll use a lot the statement like x1 and xn are IID, independent, identically distributed, which will mean that all xk's have the same distribution. Say all of them are Bernoulli 0.5, or all of them are normal with parameter 0, 1, and they are independent. IID will mean independent, identically distributed, meaning that xk's are mutually independent and they are identically distributed. Okay, now in terms of after definition of mutual independence, let me write that in the case of discrete random variables in terms of joint PMF, and in the case of continuous random vectors in terms of joint PDF. So if xk's are discrete, then they will be independent, that is mutually independent, if their joint PMF, so probability that x1 is small x1, x2 is small x2, etc., xn is small xn, is the product of marginal PDFs for all possible values of x1, x2, xn. And if x1 to xn are jointly continuous, then they will be independent if and only if the joint PDF can be written as a product of marginal PDFs for x1, x2, xn. So this is a straightforward generalization of the property we had for two random variables. Now, important problem. This is important because of applications in statistics and also in probability theory and in different places. So assume x1, x2, xn are IID, that is independent, identically distributed random vectors, random variables, with the common CDF f of x and PDF f of small f of x. What that means, so the distribution of x1 is described by this CDF and this PDF. So the derivative of capital F is small f. The distribution of x2 is again described by that. Maybe this is, say, uniform CDF, uniform 0, 1 CDF. This is uniform 0, 1 PDF. And all x1, x2, xn are uniform, say. Let's solve for the general case. So what is the problem? Problem is to find the CDF and PDF of maximum of that random variables and minimum of that random variables. So usually students say that the maximum will be one of them, say x2, and the distribution of x2 is with CDF f and PDF of f. So we have found the CDF of u is f. But this is not correct. Well, when you are calculating the maximum, then let me give with not random things, but with just ordinary functions. If I will take two functions, say if I will take sine function and if I will take cosine function, say over 0 to pi, then in some region, for some values of x, cosine will be the maximum. In some values of x, sine will be maximum. So the maximum, if I will draw the maximum, that will have this form. So this is that maximum of sine and cosine over 0 to pi. So sometimes it is this, sometimes it is that, and we cannot describe just by one random variable. So to solve this, we are doing the following. So I'm starting from calculating the CDF of u at some point x. So by definition, this is the probability that u is less or equal than x. And this is the probability that, because u is the maximum of x1 to xn is less or equal than x. And because the maximum of x1 to xn is less or equal than x, that means that all xk's are less or equal than x. So if the maximum is less or equal than some number, then each of the terms here is less or equal than that number. x2 is less or equal than that number, etc. xn is less or equal than that number. Now I'm using xk's are independent. Because xk's are independent, I can write this as a product of individual probabilities. So here I have and. I can write ends as products for independent case. This is the use of independence. Probability that xn is less or equal than x. Now, this is the CDF of x1 at the point x. But CDF of x1 is f of x. So this is f of x. This is the CDF of x2 at the point x. But CDF of x2 is again f of x. So I will have another f of x, etc. And I will have another f of x here. So I will have at the end f of x to the power n. The CDF of u is the nth power of CDF of each of x case. Now to find the PDF, we will differentiate this. So fu at x is the derivative of capital Fu, and this is equal to the derivative of this. So n times, this is a composite function, n times f of x to the n minus 1 times the derivative of this, but the derivative of that is small f. So this is the formula to calculate the PDF of u, PDF of maximum, using the PDF of each of these random variables. Now for the minimum, we'll do the following. So this is standard. Again, I am starting from the CDF of v. Probability that minimum of x1, x2, etc., xn is less or equal than x. So in fact, this is not so easy to write. I need to write x1 is less or equal than x, or x2 is less or equal than x, or, but if I will have union of several events, then I need to use that inclusion-exclusion formula, which is not so easy to deal with. So I'm using another trick. So I'm writing 1 minus, I'm passing two complements. 1 minus the probability that minimum is larger than x. If the minimum is larger than x, that means that all of them are larger than x. Now I can separate that. So all of them are larger than x means x1 is larger than x, and x2 is larger than x, and etc. Xn is larger than x. So I will have 1 minus the probability that x1 is larger than x. Here I'm using independence, times probability that x2 is larger than x, etc. Probability that xn is larger than x. To calculate this, I am passing again to complements. So probability that, probability that, say, xk is larger than x, this is 1 minus the probability that xk is less or equal than x. So this is equal to 1 minus f at x, the point x. For all xk's, the CDF is f, the same f. So I will have this is equal to 1 minus f of x for this, and another 1 minus f of x for that, another 1 minus f of x for this to the power n. So the CDF of v is 1 minus f of x to the n. Now to calculate the PDF, I need to calculate the derivative of that. So I am calculating that derivative. Fv, the PDF of v is the derivative of CDF. And this is equal to the derivative of this. So minus sign, the derivative of 1 is 0, of course. Minus sign, the derivative of this, n times 1 minus f of x to the n minus 1 times the derivative of inner function of this function. This will give minus sign, so plus here, and the derivative of capital F, which is small f. So this is the formula to obtain the PDF of minimum. And R is asking to do some simulations to visualize this result. Okay, I can do that. Recall that in the previous case I have obtained the following. So for u, I have obtained f of u at x is n times f of x to the n minus 1 times f of x. So this was for u, the PDF of u. Now let's take xk's are all uniform from 0 to 1. If they are uniform from 0 to 1, then for x between 0 and 1, fu x will be n times f of x is x. Let me just recall what is the CDF for uniform 0, 1. So it is equal to 0 if x is less than 0, x if x is between 0 and 1, and 1 if x is larger than 1. So if x is between 0 and 1, this will be x. I will have x to the n minus 1, x to the n minus 1, times the PDF of uniform, and PDF of uniform is 1. So I will have this just. So if I will take uniform, then I will have n uniforms. Then I will have n times x to the n minus 1. So let me take, say, 3 uniforms. So n is 3. I will obtain 3 times x squared for the PDF of u. Let me check that for in R. Yeah, so I can close this, move to R. Okay, so open new R script and write it here. So what I'm doing, I'm generating 3 uniforms, independent uniforms, then calculating maximum. N is say 1000, 3 uniforms, x1 is R unif, and 0, 1, no need for writing that. Then I'm copying. If I will run this 3 times, I will have 3 independent copies of uniform numbers, and 3. Now I'm calculating the pointwise maximum. So this is a vector, this is a vector, this is a vector. I want to find the maximum of first element, then maximum of the second element. That is done in R by using pmax, parallel max. Pmax command is doing that calculation. Say x1, x2, x3. If I will run this, I will have x, which is 1000 size element. Okay, it is, well, the maximum of these 3 numbers, 8, 3, 2, were rounded to nearest decimal. The maximum of these 3 numbers, which was 0.87, etc. So I have that x. To find the shape of the PDF, I'm doing histogram. I'm plotting histogram. So histogram of x. Frequency is false. Not to have the number of elements, but relative frequencies of elements. Number of elements in the bin divided by the total number of elements. And here breaks number of bins. Let me increase to have more close approximation. So I will have this kind of picture. Okay, so let me first increase the number. So I'm increasing. I'm adding a color. Color is equal to, say, cyan. Selecting everything and running Control Enter by hitting Control Enter. Now I have this picture. Let me check if this is giving exactly the PDF or approximation, not exactly, of course, approximation for that PDF by adding that PDF, theoretical PDF, to this graph. So theoretical PDF was 3 times x squared. I want to draw the graph of that. So T is running from, it is a sequence, sorry, something is wrong. Yeah. Sorry. From 0 to 1, and by step 0.01, and say y is 3 times t squared. So this will calculate that PDF value at that point. Now I want to add to this plot. So I'm keeping the old plot, par new is equal to true. By this I'm keeping the plot, old plot, and adding plot t, y, type is line. I'm adding by lines. I'm doing that line with this 2, color is red, say. I will have this kind of graph, but not exactly correct because I have some mixed numbers here. So let me correct that things by adding x limits here and y limits. So x limits is x is from 0 to 1 and y is while lim is from 0 to 3 maybe. Yeah, while lim is from 0 to 3, and I will add this also for the other graph. So I'm copying and adding here. Okay, I need to run this. I can select and run everything. So Control Enter. Now let's see. So you can see nice approximation. Maybe if I will increase this number, so 30,000. Yeah, so this is what simulation, computer simulation, R simulation is giving. Okay, let's move back to our problem. So we have solved this. These two random variables are important in statistics and applications. They are denoted by x sub 1. So they are denoted by in this way. And v is denoted by x sub n. And they are called the first order and nth order statistics for these numbers. Later you will learn about that order statistics in statistics course. Now let's talk a little bit about the distribution of sum of independent random variables. Up to this point in our previous lectures we have considered this kind of problems. So find the distribution of x plus y given the joint PDF of x and y. Now we want to do the same problem. We want to find the distribution of z given the distribution of x, given the distribution of y, and knowing that x and y are independent. So in the independent case, we want to find the distribution of the sum. By the way, the central limit theorem and the law of large numbers will both talk about the distribution of this kind of sum, where x1, x2, xn are IID, so they are independent. So we have independent sum of random variables, and they all have the same distribution. Later we will learn about this central limit theorem and law of large numbers. But at this moment, let's talk about sum of two random variables. So I want to go back to the distribution of sum of random variables, but for the case when we have independence. So z is the sum, and assume that x and y are independent. If x and y are discrete and independent, then the probability that z is taking some value z is the same as x plus y is taking that value z. And we need to consider all possible cases when x plus y is z. We need to consider all possible values for x, xi, small xi, possible value for y, yj. Take all that numbers that are giving exactly z, and for that cases add all probabilities. This was from our last lectures, nothing new here, but new is the continuation. Because of independence, we can write this joint PMF, joint probability, as a product of individual probabilities. And we can even write in the following way, yj, I can express yj from here. So yj is z minus xi. So we are calculating yj and plugging, instead of this, we are plugging z minus xi. So we are calculating the sum over all possible values of x, xi, over the probabilities, over this product of probabilities, where we are taking the probability that x is xi times the probability that y is that z minus xi. Z is this number we want to calculate the probability of which. Okay, and one note here. The note is that this sum is called convolution of sequences this and that, of this sequence and probability that y is equal to yj. in Armenian convolution sounds like patet. Okay, so what is convolution? Convolution is very useful, and in many applications, even in machine learning, we have convolutional neural networks, CNNs, etc. If I have two sequences, just let me write that convolution, say AN and BN. I want to find that convolution. Convolution is something like this. Convolution at the point N is A1 B N minus 1 plus A2 times Bn minus 2 plus A3 times Bn minus 3 plus etc. up to say maybe An or An minus 1 B1. This sequence Cn is the convolution of An sequences An and Bn. And we have this kind of formula, almost this kind of formula for calculation of this PMF. Of course, usually we are not remembering this formula to calculate this probability, but we are every time using the idea to obtain that, using the independence to obtain that. And moving forward, for continuous random variables, so if we have x and y are jointly continuous, they are independent, and we want to calculate the distribution of z, so PDF of z in this case. So PDF of z is written as this integral of joint PDF from minus infinity to plus infinity, but here the first coordinate is taken t, the second coordinate is z minus t, z is this number, z is fixed here, and we are integrating over t, so integrating over a line. And what is new? This is not new, we had this, even I have a proof for this, but what is new? If we have independence, then the joint PDF can be written as a product of individual PDFs. So this joint is marginal of x at point t times marginal of y at point z minus t. And this is called the convolution of functions fx and fy. Say if we have two functions, let me give the general case. If we have two functions f and g defined on real line, then the convolution of that function, sorry, not numbers, convolution f star, this is star g, at some point z is the integral from minus infinity to plus infinity, f at some t times g z minus t dt. Again, this has many applications. In particular for Fourier analysis, this is important, very important. Okay. So some problems. Assume that x is Bernoulli, y is Bernoulli, x is Bernoulli 0.3, y is Bernoulli 0.5, x and y are independent. Find the distribution of the sum. So let's solve this. So x is taking values 0, 1 with probability 0.3, 0.7, and y is taking again 0, 1 values and 0.5, 0.5, these probabilities. Now I can make that table of z. I was thinking to first writing joint PMF for this, but we can avoid that. We can do that calculation in the place. So z can take, z is x plus y. So x is taking two values 0, 1, y is taking two values 0, 1. So z will take three values. It can be 0, so 0. It can be 1 or 2. Now I need to calculate the probabilities. Probability that z is 0. This is the same as probability that x is 0 and y is 0. The sum is 0 can happen if only two are 0. And this is because of independence. I can write that this is because of independence, say x is 0 times probability that y is 0. And probability x is 0, 0.7, 0.5, so 0.35 here. Similarly, what it means that z is equal to 1. So this can happen if one of them is 0 and the other one is 1. So this can happen in this case or this case, x is 1, y is 0. Because of independence again, I can write this, I can separate these two probabilities, and I will have probability that x is 0, 0.7, times probability that y is 1, 0.5, plus probability that x is 1, 0.3, times another probability that y is 0, another 0.5, not another probability that y is 0, because this is the first time we are meeting y is 0, but the probability is 0.5. So this will give 1 times 0.5, so 0.5. Well, I can calculate this by just by using 1 minus this sum, and that will be 0.15. Or you can write probability that z is 2. Z is 2 means x is 1 and y is 1. X is 1 with probability 0.3. Again, this probability can be written as a product of probabilities because of, again, independence. Now this is 0.3, this is 0.5, so 0.15 is a product. So we have calculated the distribution. This is the distribution of z. Several important examples. So the first one about Bernoulli ID random variables, or maybe IID because they are independent and identically distributed. So what is the problem? X is Bernoulli P, Y is Bernoulli P, and they are independent. We need to find the distribution of their sum. So X is taking two values 0, 1, P, 1 minus P, and Y is taking the same values with same probabilities. Now Z is X plus Y, so it is taking values 0, 1, 2, and now we need to calculate probabilities. Similar to the previous one, but we will find some nice formula for that. So probability that Z is 0 is in the case when X is 0 and Y is 0. And this is the product of individual probabilities that X is 0 times the probability that Y is 0. X is 0, 1 minus P, and Y is 0, 1 minus P. So we will have 1 minus P squared here. Probability that Z is 1 is the probability that X is 0, Y is 1, or X is 1 and Y is 0. And this is the probability that X is 0 times the probability that Y is 1. Probability X is 0, 1 minus P, Y is 1, P. So I will have 2 times P times 1 minus P, because this is equal to that, and I will have 2 times that. Okay, 2 times P times 1 minus P. And for 2, I will have Z is 2 only if X and Y are both 1. X and I are both 1. That means the probability of that is P times P, so P squared here. What is important? The important thing is the following. So I'm erasing this. Now, this distribution is one of our standard distributions. and this is, you can guess that, Z is binomial with parameters n is 2 and p is p. So if we are adding two Bernoulli p random variables, independent random variables, we are obtaining binom 2p. So explanation of this. What is showing y, what is showing x, and what is showing z? So x was showing, x is Bernoulli, that is x is 1 if we have success in one trial and 0 if we have failure. Y is for the second trial. So we are doing two trials. The first is described by x, second is described by y. Y is 1 if in second trial we have success, and y is 0 otherwise. And trials are independent, so x and y are independent. And I'm calculating in that two trials, I'm adding x plus y, so I'm calculating this is the number of successes in two trials. So what we know that the number of successes in two trials, two independent trials, is exactly binomial 2p, not pi. This was just by description or definition of that binomial distribution. Now, if I will erase this and look at the part B, assume we have n identically distributed independent identically distributed random variables, IID random variables, such that xk is Bernoulli p. So x1 is Bernoulli p, x2 is Bernoulli p, xn is Bernoulli p. That is, I'm doing n trials. xk is showing whether in the case trial I had success or not. If this is 1, my case trial was success. Otherwise, it was failure. The probability of each success is p. Success in each trial is p. And they are independent, so I'm doing trials independently. So what will show the sum of that x case? So the sum will show how many ones I have here. So x1 is either 0 or 1, 0 or 1, 0 or 1. So this sum is showing how many ones I have. That is how many successes I have in that n trials. That means that the distribution of x will be binomial with parameters n and p. So this is important. So binomial can be decomposed into sum of independent Bernoulli random variables. Well, you can formally prove this also by using induction, mathematical induction, but I will note that explanation is enough. Okay, so another example of that form, x is binomial np, y is binomial mp, this is n and that is m with the same p, and x and y are independent. Find the distribution of their sum. So I'm thinking like this. X is decomposed into x1, x2, xn, n Bernoulli, xk's are Bernoulli, IID, Bernoulli, p random variables. So x1 is showing whether I had success in the first trial, in the second trial, in the nth trial. If I am adding, I am calculating the number of successes in n trials. The trials are independent, so I have IID random variables. Now, y is decomposed, it is binomial, into a sum of y1, y2, etc., ym. Yk's are IID, again Bernoulli P. So because x is independent of y, we can have that x, well, we will have that this x case or y case are independent of each other. So because they are independent of each other, then z, the sum, will be the following: x2 plus xn plus y1 plus y2 plus ym. So I will have Bernoulli P, Bernoulli P, Bernoulli P, Bernoulli P, Bernoulli P, and the number of these is n plus m. They are independent, so I will have that z is binomial n plus m p. This is the result, and you can prove that without passing to that Bernoulli random variables. You can prove that mathematically rigorously also by using the convolution formula for the PMF of sum. Okay, so x is Poisson, y is Poisson with different parameters, and x is independent of y. So find the distribution of z, which is x plus y. So x is taking values from 0. Let me just recall what was that definition of Poisson distribution. So x is taking the value k. K can be 0, 1, 2, etc. with probability e to the minus lambda 1 times lambda 1 to the power k over k factorial. K is running from 0 to infinity. And for y, I need to change to lambda 2. Now I want to find the distribution of z, which is the sum. So I'm writing the following: probability that z is equal to some n. So what can be the values of z? X can take 0, y can take the value 0, this will be 0. Negative numbers I will not get. If x is 1, y is 0, I will have 1. 0, 1, I will have 1. 1, 1, I will have 2. So z will take all non-negative integer values. And I want to calculate the probability. What is the probability that z is equal to n? So this is equal to, in which case I will have z is n. So z is n means either x is 0, y is n. X is 0, y is n. Sum will be n. Or maybe x is 1, y is n minus 1. Plus etc. So here I'm writing that convolution, in fact. If I will write in the product form, that will be a convolution. So maybe x is n, not xn is n, but x is n, and y is 0. Okay, so I will write this in the form of a product. Because of independence, I can write as a product. So product of probability that x is 0 times probability that y is n. And I can write that in a form of a sum. K is running from 0 to n. Probability that x is equal to k. Probability that y is equal to, you can see that always we have sum is n. Because we have just considered all cases when this is equal to n. All possibilities, 0, n, 1, n minus 1, 2, n minus 2, etc. So n minus k. I need to write n minus k. Now if I will plug the PMFs for x and y, k is running from 0 to n. So probability that x is equal to k is this much, e to the minus lambda 1 to the k over k factorial times this probability e to the minus lambda 2 times lambda 2 to the n minus k over n minus k factorial. Now I am simplifying this. I am taking out this constant e to the minus lambda 1 plus lambda 2. Then sum. I will have lambda 1 to the k, lambda 2 to the n minus k, and in the denominator I will have k factorial n minus k factorial. Let me add n factorial here. And I will divide that again. So I'm not changing, multiplying and then dividing by n factorial. N minus k factorial times lambda 1 to the k, lambda 1 to the k, times lambda 2 to the n minus k. So let me write it from this part. I am almost done. So this is equal to e to the minus lambda 1 plus lambda 2 over n factorial times the sum. In the index of the sum is running from 0 to n. K is running from 0 to n. This is binomial coefficient, n choose k, lambda 1 to the k, lambda 1 to the k, times lambda 2 to the n minus k. And you can see that this is just the binomial formula for lambda 1 plus lambda 2 to the n. So I will have e to the minus lambda 1 plus lambda 2 times, this is lambda 1 plus lambda 2 to the n in the binomial form over n factorial. So we have obtained that this is equal to that. In other way, you can see that z is another Poisson random variable, but with parameters lambda 1 plus lambda 2. Probability that z is n is e to that minus that power times that power to n over n factorial. So the result is z is, if x is Poisson lambda 1, y is Poisson lambda 2, and if they are independent, then z is Poisson lambda 1 plus lambda 2. And you can think about interpreting this as a number of events. So we have some events and then another number of events, and we're calculating the sum of that two events, say hurricanes and other things. We are calculating the number of that in a year or something like that, and you can interpret that. You can interpret this result by using that number of some events interpretation for Poisson. Okay, so let's move forward. Assume x and y are uniform in 0, 1, and they are independent. So find the distribution z of z, x plus y, and then obtain the shape of that distribution in R. Okay, so in fact finding the sum distribution in the continuous case is not so easy, even having this simple distribution. Well, the uniform 0, 1 is one of simplest distributions. Even in this case, calculating this is not so easy. Let me just quickly describe what we are doing. So I'm solving this A part, B is with R. So X is uniform, Y is uniform. We can write the PDF of f of x, which is f of y at the point x, because they are both uniform 0, 1. 1 if x is between 0 and 1, and 0 otherwise. And they are independent, so I can use joint is the product of marginals. Now I'm writing the formula for calculating the PDF of sum, z is the sum, at some point z. So this is equal to the integral. So I'm calculating the convolution. Convolution is integral from plus infinity, not plus infinity, of course, this is minus infinity, from minus infinity to plus infinity of convolution of this and that. So convolution of this and that is the following: fx, say at x, times fy at z minus x. So this is z, the same z is here, x minus x dx. So this is that convolution formula. Okay, now we will have that f of x is 0 outside of 0, 1. So I will integrate, x is changing from 0 to 1 here, 0 to 1. Otherwise I will have 0 here and the integral will be 0. So integral is over 0, 1, fy at z minus x dx. Well, the problem is that this is also at some portion, if I will plug here z minus x, I will have, for some values it is 1, otherwise it is 0. So I need to integrate over that values 1. So I need to intersect that range with 0, 1. That is a little bit hard part maybe of this problem. So let me solve this by considering several cases maybe. 0, 1, 2. First I want to write when this is non-zero. So this is non-zero in the case when z minus x, the z minus x is between 0 and 1. 0 and 1. So for x this will be, I'm solving for x. I'm bringing to this side, x is less or equal than z, and this is larger or equal than, if I will bring x to this side, z minus 1. I will have z minus 1. Okay. So let's consider several cases. If z is less than 0, then x is less than 0, I will have, well, what was this again? This is the part where this is non-zero, this is 1. Outside of this interval, f of y at that point, z minus x, will be 0. If outside of this, or maybe I will write this is the case. So this is non-zero. So if z is 0, then x is less than 0, but we are integrating x is from 0 to 1. So in this case I will have 0. So fz, that integral, will be 0. Also, if z is larger than 2, then from this part, x is larger than 1, but we are integrating from 0 to 1. So f is non-zero, this integral, integrand is non-zero from z minus 1 to z, but z minus 1 is larger than 1, so it is 0 from 0 to 1. So I will have 0 here. So fz is 0 if z is less than 0 or z is larger than 2. Now let's consider cases for z where z is between 0 and 1 and 1 and 2. So I want to erase maybe this part. I will erase also this part. Just remember that we are calculating fz at point z. This integral is fz at point z. So if z is between 0 and 1, z is here. So I am drawing this region from z minus 1, this is z minus 1, the length is 1. From z minus 1 to z, this is non-zero. This is in fact 1 at that region. Fy was either 1 or 0, so if this is not 0, it is 1. So, but I am integrating, here my function is 1, but I'm integrating from 0 to 1. So I will integrate from 0 to z. So fz small z is integral. In fact, I am integrating from 0 to z because my fy is 0 here. So from 0 to z, 1 dx, and I will have z. If z is between 1 and 2, say I am erasing this z, erasing this, and writing the second case. Say z is here. This is z minus 1. My function is 1 here and 0 outside, but I am integrating from 0 to 1. So I am integrating from z minus 1 to 1, in fact. So fz at the point z will be integral from z minus 1 to 1 of 1 dx. So this will be 1 minus this, so 2 minus z, if z is from 1 to 2. And combining all this, I will obtain the following. So combining everything, I will obtain the following thing. So fz at the point z is equal to z if z is between 0 and 1, 2 minus z if z is between 1 and 2, and 0 otherwise. And the graph of that will be the following: x, y, z from 0 to 1, so from 0 to 1 z, this is 1, this is 1, then 2 minus z, I will have this is 0.2, and 0 otherwise. So the sum of two uniform independent random variables, uniform 0, 1 random variables, has this PDF, so rectangular distribution, the sum of two uniforms. You can try to do that with 3 uniforms, 3 independent sum of uniforms, x plus y plus say t, or x plus y plus z. Okay, so the second part is obtain the shape of distribution in R. By the way, we can obtain the shape by using R. That will not give the function, but that will give the shape. So I'm erasing this. Okay. Another R script. So what I want to do, very easy to do that in R. So n is, well, I'm not writing correctly. N is say 1000. X is R unif from 0 to 1. Independently, I am choosing y unif, again n. Z is the sum of them, x plus y. And I am plotting histogram, just this. Histogram of z, breaks, maybe breaks is 50, frequency, sorry, is equal to false. Yeah, maybe color is cyan. Yeah, something like this. Okay, so let me increase this number, 10,000, run everything, or maybe 50,000, 40,000. You can see that we are obtaining that rectangular shape for our, you can try to add that theoretical PDF to see that this is fitting pretty well to that. Okay, this much for this problem. Let's go back to our lecture. So the next one is example 33.22. Assume we have two normals. X is normal with mu1 sigma 1 squared, y is normal with mu2 sigma 2 squared, and x and y are independent. Then one can prove that x plus y, the sum of two normals, two independent normals, is again normal with mean mu1 plus mu2 and variance sigma 1 squared plus sigma 2 squared. So a mean is the sum of means, sum of this and that, and variance is the sum of variances. In the case when x and y are normal and independent. I will not prove this, this is technical. I'm just giving as a fact for you. And another thing is, assume that we have bivariate normal, x, y is normal with this mean and this covariance matrix, then x and y will be independent if and only if this and that are zeros. Well, because we have symmetric matrix here, just one of them is zero. So x and y are independent only in that case. So if I will write something like this, xy is normal with -3, 2, say 5, 0, 0, 3, then you will have that x and y are independent. Because this is 0, this is 0. And one thing to think about, can you prove by definition, by our definition, that x is dependent on x or x is dependent on g of x? G is some function. Okay, this much. Thank you. Bye.